Hi everyone, thanks for being here, and it's a pleasure for me to introduce Vidhi Tailor to you. Vidhi is a PhD student at the University of Bologna. She's in the third year, which is last year of PhD there. She did her bachelor at the University of Mumbai in physics, and then the master in physics as well. Same university, with a thesis on circumnuclear disks in massive stars. Right? High mass. Well, and then she stayed not really in the topic because she moved to galaxies when she started her PhD a couple of years ago in Bologna under the supervision of these three guys. Since I collaborate with them, they thought, okay, let's send her to Mexico for this nice experience. And now she's here for a couple of days more. She'll be here since January. She will leave next Monday, and she's going to present the results from her first paper and the results from the next two big paper, which will soon be out. So, thanks.
Hi everyone, thank you for coming. I'm Vidhi. So as Jacopo said, I work with interstellar medium in my thesis, and today I want to focus on the dust component of the interstellar medium, which I heavily studied in the last 2 years. So to first give a very broad context of how the periodic matter cycles through the ISM and how they are interdependent, we start with the gas phase, which, as we know, would cool down and collapse to form stars. And these stars, over their lifetime, would evolve and create heavy elements through nuclear synthesis. And at the end of their lifetime, through feedback, would then return these heavy metals back into the ISM in the form of gas-phase metals and also small dust grain seeds. So once these metals are in the ISM, they don't stay in the gas phase, but a huge fraction of them would again condense onto these smaller grains and would give rise to a larger dust grains. And these dust grains then interact with the different ISM components and affects various thermal and physical properties. So the dust mass in the ISM makes up a very small fraction of the total ISM mass, which is about 1%, but they play a disproportionately important role in the thermal and the chemical evolution of the galaxy. So the first most important is that the dust grains would absorb the optical and the ultraviolet emissions from stellar sources and reprocess them, re-emitting them into infrareds and submillimeter wavelengths. But not only does it affect how we observe the stellar emissions, it also impacts on the chemical properties of the ISM. So dust is responsible for cooling the gas. So the efficiency of gas cooling would then directly be connected to the star formations. It also plays an important role in the chemistry, and particularly in formation of various molecules, including molecular hydrogen and carbon monoxide, by providing them a surface on which they could grow. And in addition to that, the dust also provides these molecules against the harsh UV radiations, against photodissociations, which would then become essential for star formation. So at any given time, the amount of dust that we see in the galaxy is the balance between three different processes that are competing against each other. The first one is the production. So the dust grains form in the cooler envelopes of the AGB stars and also in the ejectors of supernova. And these the amount of dust grains that is formed from these stellar sources are not sufficient to explain the large amount of dust mass that we observe. So for this, we come to the second process, that is the grain growth in the ISM. So as I said before, the metals in the dense ISM phase can condense onto the dust grains, where they make the dust grains grow in size and mass. And these dust grains can also be destroyed by various processes, which includes shocks from supernova explosion and also through sputtering. So when we observe the galaxy mass, we basically determine how these three processes compete against each other, and this could give us insights into the chemical evolution of the galaxy. So here today I want to answer two broad questions about dust. First is on the energy side, that is what sets the dust temperature or what heats the dust. So this is of course related to the dust properties themselves, which comes with the beta factor here, but also by the radiation that is exposed to from the star, which can be parameterized by this parameter Q over here. And the second question I want to ask about is what is the dust mass budget of the galaxy? So how much dust there is relative to other baryonic components like stars, gas, or metals in the galaxy. So we first look at the first question on the dust temperature. So the dust temperature is set by a combination of two things, which is the grain properties themselves and grain properties themselves, which includes the composition of the grains as well as the grain sizes and the interstellar radiation fields that they are exposed to. So there exist very small grains which are stochastically heated by high energy radiations, and this could lead to them rising up to very high temperatures of about 1000 Kelvin. And in contrast, we have the larger grains which lie in a more relatively stable equilibrium with the surrounding radiation fields, and they lie at the temperatures of about 15 to 30 Kelvin. And these large grains generally emit in the far infrared side of the spectrum. So for my work, I focus mostly on these large grains in the far infrared division.
One question. Could you tell us what U is? What is U?
U is the parameter that basically defines what is the radiation field strength in the ISM. So how strong is the stellar radiation that hits the dust?
Is it some ratio of some?
Yeah, it's normalized and, from that to the radiation is then normalized to the radiation in the solar neighborhood to get the values of 1 to okay. So what heats the dust? So as I said, there can be several components, sources that will heat the dust, amongst which are radiations from the younger stellar population to radiations from much more evolved stars. And also in some cases, we see AGNs contributing to heating of the dust in this cold dust regime. So here I show an example of a study that was done by Bendo, where they look at different color temperatures of these cold dust and correlate them with tracers of different stellar populations. So for example, H alpha traces the younger stellar population, so the star formation, and the 3.6 micron traces the old stellar population. So what this shows is that the temperature that we observe, or the distribution of the dominant heating source that we observe, is also somewhat dependent on the metallicity that we observe. So for example, here, when we look at the shorter wavelength color temperature, we can see that the higher dust more strongly correlates with the star formation or the younger population distribution. Whereas when we look at for the same galaxy, when we look at the color temperatures belonging to the longer wavelengths, the distribution is more closely linked to how the older stars are distributed. So what it tells us that the heating is somewhat mixed between different populations and different sources, and both of them have some significant contributions to the work. So again, here I show an integrated study which drives the same point. So on the y-axis, it basically measures the red portion, measures the amount of energy that is absorbed by the dust from the older stellar population to reach the temperature, and the blue from the younger stellar population. So and the x-axis is the morphology of different galaxies. So if we look at very early type galaxies, we see that the contribution is dominated by the older population, whereas as we move towards the spiral galaxies, we see an increasing contribution of the younger population, but the older population still has a much significant contribution. So this duality, like where both of these radiation contribute, has an important implication to certain assumptions. So we generally make use of the infrared luminosity or the dust emission to calculate the star formation rates for various galaxies. And if this is true, and that the Earth stellar population does contribute a lot to this emission, then that relation might not always be valid or correct to use. And this becomes increasingly important in the centralmost parts of certain galaxies, as I'll come back to it later in the next few slides. So to study this heating sources in the galaxies, I need four things. One, which is the dust temperature, the dust masses, which are the dust properties, alongside of something that traces the younger population and the older population. So for this, we use the Dustpedia subsets. So Dustpedia is a very large collaboration of about 875 nearby galaxies, and these all galaxies are observed by Herschel. But alongside Herschel, it also has a very large repository of multi-wavelength data from various bands. So from this big sample, we select a sample of 18 galaxies, which are large, spiral, and face-on. And the selection criteria for them was that the galaxies are sufficiently large enough in the sky that we can make result observations at the worst Herschel resolution, which is at 500 microns, which has a resolution of about 36 arcseconds. So at this resolution, the physical scales that I can probe for this 18 galaxies varies between 0.3 to 3 kiloparsec. So just to show an example of how the data looks like. So first, I showed an example for M74. So here we take the Herschel far-infrared emissions, and then we do Segal SCD fitting codes, and we do it at each individual pixels of the galaxy. So from that, we directly get the dust mass maps as on the right. And for the dust temperature, the Segal gives an output of this U parameter, which is the interstellar radiation field. And from this, we can convert it to the observed temperatures, and we get this map. So for the dust map, we see that the dust mass is very centrally concentrated and also has a significant distribution along the spiral arms. Whereas in the dust temperature, even though it is varying or decreasing radially outwards, we see a much more clumpy structures with very bright clumps around here. And these clumps correlate with the star formation activities in this map, in this galaxy. So here we use star formation, which essentially traces the younger population. And to calculate the star formation rates, we use two bands, which is far ultraviolet and infrared. This combination allows us to look at both unobscured and obscured star formation rates. Yes, so from this, because we use the far infrared emission, the characteristic timescales for these stars are then about 100 million years. And similarly, we use the stellar mass maps to trace the older stellar population, which shows a very smooth decrease radially for this galaxy. We use two infrared bands from IRyA here. The stellar mass is mainly calculated using 3.6, where 4.5 helps to correct for the non-stellar component emissions such as PAHs, while determining the stellar mass. So again, back to the question of what contributes to the dust heating and in what ratios. So for this, we do two methods. So for the first method, we simply study the correlations between the properties. That is correlation between dust temperature and star formation rate and dust temperature and stellar mass. So we do this for each individual galaxy. So here, each point is a pixel in this respective galaxy. So here, for the example of IC342, we see that the correlation with star formation is very weak compared to the correlation that we find for the stellar mass. So in this case, the dust temperature is more prominently traced by the older population by this method. So we can do this for all the 18 galaxies, and here I summarize the results for all of them. So on the y-axis, I have the correlation between dust temperature and stellar mass, and on the x-axis, I have the correlation between temperature and star formation rate. The black dashed line is 1:1 ratio, and each point here is the galaxy, and the star symbols are symbols where in the galaxies an AGN is present. So we see that for most of the galaxies, we see that for most of the galaxies, both of the ratios shows moderate to strong correlations. And an important thing here is that the spread of correlations for the temperature and the stellar mass is very narrow and generally lies around this 0.7-ish for most of the galaxies. This would imply that the contribution from the older stars is always present across all the galaxies, and that it has a much more diffused, longer, it maintains the radiation for a much longer time. So for the second method, we test a relation between the dust temperature and the dust mass surface densities. So for this, we use the arguments that were given first in the Toma. So the hypothesis is that we assume that this relation between temperature and the dust mass would exist if the temperature that we see was driven by the younger population. So the main assumption here is that the entire infrared luminosity that we observe comes from this younger stellar population, and that this emission can be described with the help of a black body function. So then if we take the Koenig-Smith law and we assume that there is a linear relation between the dust gas and the dust mass surface densities, then we come to this relation between dust temperature and dust masses. So here we can fix these constant values of n and beta. So for the value of n, we fix it to this value, which was derived in Casasola, who studies the same set of the 18 galaxies that I studied and gets the slope where all the galaxies are put together and are studied at the common resolution scale of 3.4 kiloparsec. And for the beta, we set it to this value, which corresponds to the dust model that we are using in our LCD fitting, which is the Themis model. So once we fit all that, the relation basically only has one free parameter, which is the normalizing constant. And what we want to test is that if the data points, if our data follows this relation, then our hypothesis would be correct, and the younger population are in fact the source that drives the dust temperature. So here I show two examples of what we find. So on the y-axis we have the dust temperature, and on the x we have the dust mass. So for the galaxy on the top, NGC 5194, the blue points here are the median values in the bins, and the black line is this expected relation trend that we want to observe. So for this galaxy, this trend is of course very clearly deviating from this expected trend, and thus for here the hypothesis is incorrect, and that we conclude that for this galaxy it has a very significant contributions from other sources like older populations or AGNs or etc. In contrast, we have this other galaxy, which is 3621. And for this galaxy, you can see that these data points are followed very well, follows the expected trend very well. And here, then, we conclude that for this galaxy, the young star does in fact drive the temperature of the dust. So similar to the plot before, here I add the information of the second method. So again, the y-axis is the correlation between temperature and mass, the x-axis temperature and star formation rates, and then the points are now color-coded with the results of the second part, where the blue points indicates where the galaxies were following the trend, and so were where the younger population was the main component responsible for the dust heating, whereas all the yellow points are where there are significant contributions from other sources. So overall, from what we gather from all of this is that dust heating is mixed between both the populations, and we cannot it has contributions from both, where the younger stars contribute more intensely in the star-forming regions, whereas the older population has a much more diffuse, extended radiation across the galaxy. And the methods more or less agree for most of the galaxies, for about 72%. But there are some galaxies here and here that show some deviations from which results are correct. So this discrepancy could be due to a few assumptions that we made. One of this could be an effect of resolution, because as we go to the coarser resolutions, we cannot resolve the individual star-forming regions very well, and this could lead for the radiation in those regions to dilute with the more diffuse surrounding radiations. The second could be that we assume a constant slope for the Kerry-Kesman law, which studies have shown that the slope could vary from galaxy to galaxies, and sometimes also it could vary within a galaxy depending on the regions and the resolution you look at. The third is the linear relation that we assume that exists between dust and gas masses. So this the dust to gas ratio is not generally the dust to gas ratio is not always constant, but it could depend on different ISM conditions, especially the metallicity of the ISM, and also depends on the efficiencies with how the grain grows and destroys. So some other important things that I would like to highlight from other studies is that so this is the same paper from Narcessian as before, and here they show that the red, so the solid color bars are the percentages of the stellar luminosity that goes unaffected and reaches as direct starlight, whereas the shaded bars over here are the fraction of luminosity of individual sources that are absorbed by the dust to heat them. And so if we look at for the spiral galaxies, we see that for the older stellar population, much of the luminosity, much of the emission that these sources give out goes unchanged across the galaxy, and only about 24 to 25% of them is being absorbed by the dust to heat them. Whereas for the younger population, they contribute up to 77% of their luminosities to heat the dust grains, and very little of us is reached to us unaffected. Another thing, there are several studies which shows detailed radiative transfer modelings of this. So here are examples of 3 galaxies. So the y-axis in all the case is the fraction of luminosity that is contributed by both population comparatively. So the red line is the contribution from the older population and blue is from the young. Similarly, here the solid line is from the young population and the dashed is from the older evolved population. And the point that I was making earlier about using infrared luminosities to trace star formation rate comes from this. So as you see in the very central regions over here, the older population does exceed the contributions in towards the dust emissions, and if not exceed, it's also at least comparable over here to the younger sources. And even as we move out, even if the contribution decreases as we move out radially, it still remains significant across the galaxy. And these studies conclude that the younger population contributes anywhere between 50 to 70% of their luminosities, 50 to 70% of the luminosities that are required to heat the dust, where the remainder is filled by the older population. So this answers, this discusses what sets the dust temperature, but I would like to move on to the second part of my question, which talks about what is the dust mass budget. In particular, what is the budget comparative to other baryonic components like gas and metals. So we can study this ratios, and since as we discussed, this dust to gas ratios does not remain constant but evolves as a function of metallicity, and also depends upon the balance set by the growth and the destruction of the dust grains themselves. So to start with, we expect the dust to gas ratios to increase as we move across the metallicity, as we move towards higher metallicity. So for example, I show you two plots which discusses this trend in gas to dust ratios instead. So this is the study by IRyA, which studies integrated galaxies, and we see that there is a very sharp, very steep dependence on gas to dust ratios on metallicity in the lower metallicity regime over here. And once we pass what they term as the critical metallicity, which lies about 8.1, this dependency quickly decreases, and we expect a more linear relation between this ratio and metallicity. Similarly, we find similar trends for the result studies, which I show here from a study by IRyA. They find a similar trend where there is a steep dependency in the lower metallicity regime, and as we hit a critical metallicity, this dependency sharply decreases to an almost linear relation, although they find different values of the metallicity. So to study this dependency of dust on metals and gas, we need additional information than what we had before. Particularly, we need information about the metallicity distribution of the galaxy. So for this, we make use of the metal-based survey, which gives us the IFU, optical IFU data cubes for these galaxies, which are spatially resolved. So we have about 9 galaxies that are common between the dust media sample that I was using before and the metal things, and 1 galaxy is supplemented by the IFU data from news. And the highlighted galaxies are then the galaxies that we consider for the next part of our analysis. And these, again, are supplemented by gas masses, which comes from things that Heracles survey. So the metal things give us a spatially resolved spectra of the galaxy, and from this we can derive emission lines of the galaxy. We then degrade this data to match the resolution of our dust, so that's why they look very clumpy. But we can then use these we can use this optical line measurements to select the star-forming regions within the galaxy using the Vidhi diagram. So the blue are the star-forming regions, which approximately lies here in the galaxy. And then we can calculate the metallicity for them using the Pelagian prescription from 2016. These are the examples of the gas components that I use. So the atomic gas data comes from the Things survey, which uses VLA 21 centimeter observations, and the molecular gas comes from the CO 12 CO observations of IRyA. So the CO emission is then converted to estimate the molecular hydrogen masses, and the total gas is then just the sum of these two gases and multiplied by this factor of 1.36, which is added to include the contributions of helium and other heavier elements in the gas. So we use the CO to convert the CO luminosity to get the molecular hydrogen masses. But this CO luminosity is not a universal quantity, and it depends on local environmental conditions, and in particular, it depends on the metallicity. This comes because of the shielding effect that I was talking about in the beginning. So as you can see in this diagram very clearly, as we go towards lower metallicity, the CO gets destroyed because in low metallicities we have less dust, which would make them more vulnerable to photodisassociate. Whereas for the H2 molecule, after a sufficient column density of H2 is reached, it can self-shield against the UV radiations and are not as prone to destructions as is the CO molecule. So as we go towards lower metallicities, there are regions where the same amount of CO would face a different fraction of the H2 mass. So as we go from here to here, the CO here would have to account for a much more stronger alpha CO, so we can get the correct H2 masses. So to see this dependency, we test 3 different prescriptions for this alpha CO. The first one is the constant factor which we get from the Milky Way, which is from Bologna. And then we use 2 different metallicity calibrations. So one of them is from Amorine, which says that alpha CO increases at a factor of 1.5 as you go towards lower metallicities. And the other one is from Shubra. The Shubra calibration gives a much more rapid increase of alpha CO as you go towards lower metallicities, and also has a relatively higher normalization factor to it. So even at solar metallicities, the Shubra calibration would trace a larger amount of H2, would give us a larger amount of H2 than the ammonia. So then we try to see the dust to gas ratio as a trend of metallicities for each prescriptions individually. So all the points are radial bins within individual galaxies. And the first panel here shows the results that we get from the calibration of the constant CO conversion factor. So as we can see, the galaxies are more or less scattered among them, but also within a single galaxy, there's a significant scatter of the dust to gas ratios. In the background, the gray points are all the dustpedia late type galaxies integrated to see how their trend lies, and the black curve is the analytical dust evolution model, which is given by Galileo. Except from the scatter, we see that these galaxies, which are at the lower metallicity end, sits at a very elevated dust to gas ratios. And when we change the prescription to Amorine, which is the weaker metallicity dependent prescription, the overall distribution of the galaxy remains more or less same. These galaxies are still higher on the dust to gas ratios. But a thing to note is that for some galaxies, we see that there's a decreasing trend in the inner regions for this galaxy, which disappears when we go to the metallicity dependent case, which can be more clearly seen in the radial profiles. So the blue is the constant conversion, and the red curve is the ammonia description. So this deviation, this rise of DGR in the central part that we get from ammonia is reflecting the fact that as we go towards the inner regions, the metallicity increases, and thus the alpha CO should increase. The alpha CO should decrease in the innermost region and give us lower hydrogen masses, and thus a higher DGR. Similarly, in the third panel, we have the prescription of sugar, which shows a very significant deviation from these both trends, where all the galaxies are more or less shifted to a very low DGR value. This is a manifestation of this higher normalization that we see over here of 8 compared to 5, and it was about 4.3 here. So this causes the sugar calibration to give us consistently higher H2 mass estimates for all the galaxies, and thus all the DGR values are shifted to much lower. So what this panel highlights that the ratios are not only dependent on the dust evolution themselves, but also are also dependent on the systematics that are used to derive them, and particularly the gas masses. And while analyzing these trends, we should also take that factor into consideration on how our assumptions affect the trends. So after DGR, we look at the dust to matter ratios, which is a similar question asked in a different way, where this DMR ratio would essentially tell us the fraction of metals that is locked up in dust compared to the total fraction of metals in the whole IRyA over here. So the total metals are calculated as the mass of the metals that are in the gas phase plus the mass of metals that are in the dust phase. That's the dust itself. So this is the integrated, this is the global trend that we see for the DMR metallicity relation from Davis. What they show is that these data points follow this yellow curve, yellow model in their description much better than the other two. And we see as the metallicity is increasing in the lower region, this causes the DMR value to increase, at which there's a very sharp increase of metallicities around 7.7 to say 8.2. And after which this essentially reaches to a saturation of DMR values. So this is where the dust, this is the regime where the grain growth in the ISM has become so efficient, and essentially saturates the amount of dust that there is. So we do the similar study as we did for the DGR. Across the 3 different alpha CO prescriptions. And again, here, similar to there, we find there's no significant difference between the constant alpha CO conversion and the marine metallicity conversion, except for here, the trends in the inner regions is much more clear. Again, when we go to clear, and also that these galaxies still sit at very high DMR values compared to where most of the galaxies sit. Again, if we compare this to the sugar calibration, the trend is very different. So instead of here it being mostly constant across at least individual galaxies, here we see a very strong negative gradient between the galaxies and also among these galaxies. Again, this is a manifestation of the higher normalization of alpha CO, and is the main driving factor that causes the DMR values to be lower for this case. So then the question becomes that what alpha CO is gives us a better description of the molecular masses, and thus what should we actually consider when studying this. So to take a look at that, we study the relation between the CO luminosity itself and the star formation rates. And if the molecular depletion timescales are constant, then this linear relation exists, that is shown in the black line. So we see that for most of the galaxies, they sit very close to this relation, so that CO luminosity agrees with what their star formation rates should be. But if you see for these two galaxies that are in the bottom, these are the same two galaxies that were low metallicity in our sample with higher DGR and DMR values. So they significantly deviate from this trend, this by a factor of 3 and this by a factor of 1.6. One of the reasons that could be that there is a strong presence of CO dark gas here. So if we look at it in the terms of the dust heating results that we were discussing before, these two galaxies, we find that the young stars drives the dust heating completely for both of these galaxies, and since they sit at a very relatively low metallicity environments, this UV radiation from young stars could easily destroy the CO molecules here and could contribute to a very large fraction of CO dark molecular gas. In contrast, we have this one galaxy here, which is IC342, which shows an enhanced CO luminosity, which is about 2.5 times higher than the relation predicts. So this could be because the molecular depletion times for this galaxy are much longer. And another way to look at it is that this galaxy has a very large central concentration of gas, and it has a central starburst, which could affect the enhanced. So this central concentration of stars and gas can then affect this CO emissivity, giving us which makes it much more luminous in the CO. So based on this, we come to the conclusion that a single alpha CO prescription might not be good for all galaxies. So we come up with a sort of a hybrid situation where for these two galaxies, we consider the Shudra prescription, which gives much better corrections for the CO dark gas. Whereas for the rest of the sample, we continue with the metallicity dependent calibrations, but for Amorine, which has a mild correction relative to Shudra.
Sorry, I had a question about that for you. The dashed line is not a fit to these data.
No.
Okay.
The dashed line is an empirical fit from this other study from Bologna, which also depends on dust media galaxies, and they find this relation there. Okay. So then when we use this hybrid prescription, where for these two galaxies we use the steeper metallicity dependent prescription, and for the rest we use the Amorine prescription, we see that the situation has resolved much better, that these galaxies trace the observed trend that was found by Amorine much better, and also the pink dashed line here is the re-emitting fit that we saw earlier, that says that there's a linear dependence between DGR and metallicity. And again, in the case of DMR, we see that most of the galaxies have now reached sort of a constant DMR values, where mean for all the galaxies lies at about 30% DMR, which is that the 30% of all the metals in the ISM are inside the dust grains. So this saturation also is explained, also lies correctly with the assumption that at these metallicities of 8.2, 8.3, which are almost near solar metallicities, there should be a saturation in the saturation in the gradient processes, and the ISM should be evolved sufficiently for them to reach this planet. Between these two plots, even though there are significant improvements than all the 3 panels before, there are still some galaxies that show deviations, which likely is IC342 over here, which its deviation much more evident here, where its inner region sits at much lower EMR value. This could again be because of its central starburst. So since it hosts a central starburst, the gas in the center could be elevated to very high temperatures and could also have very high dispersion velocities. And this could cause effects on the alpha CO itself. In fact, there are studies that show that for this galaxy, metallicity alone calibrations are not favorable, and something that takes into account the density as well as the metallicity gives us much better results for this galaxy. Except this, there is also these 2 galaxies which always sit at the top of the relations. So the alpha CO uncertainty aside, this can also be because for these 2 galaxies here, they show a very low gas mass fractions, which is defined by this. And this low fraction would then imply that these galaxies are more chemically evolved, and so more metals have the time to be accreted onto the dust planes, and thus they sit at very high values over here. Another point to note that could affect this relation is the dust mass themselves. So the dust mass depends upon factors of the grain properties itself, that is the emissivity of the grains could vary, and there are studies that have shown that this emissivity also varies across the galaxy and could also differ between what model we assume. So what do we learn from both of these trends? So we use a dust evolution model from IRyA, which models M74 to study these trends. And the important thing to note here is that the models are specifically designed only for M74, but we use them here as a more representative states for galaxies that have similar properties to M74, and thus they should only be assumed that if a galaxy property is similar, then these conclusions are true. So IRyA tested different prescriptions for the grain growth timescales in the ISM, for the dust production timescales, as well as the dust destruction timescales. And out of this, they found that these 2 models were the best fit to their data. And these 2 models have similar dust production timescales, but they differ in how they define the dust accretion and dust destruction over here. So quickly, the model 5 is shown in the blue curves, and the model 9 is shown in the maroon curves. The model names are similar to that of the IRyA paper. And we see that among these 2 models, model 5 provides a much closer description to where our data lies. So for the DGR, even though there is some normalization offset, it follows the slope and the trend very well, whereas the slope for the model 9 is much steeper. Whereas for the DMR, the model 5 essentially traces this plateau that we observe for the part of the galaxy, and model 9 shows a variation with the metallicity that we do not observe. So we say here that model 5 gives a much better approximation for what is happening in our galaxies. So as I said, they have different prescriptions for all the timescales between production, growth, or accretion, and destruction. So in the first plot, they show how the ratio between the production and the accretion evolves as a function of the peptide. where the model 5 is in black and model 9 is in brown. So we focus on the model that we, or model 5, since it gives us a better description. So we see that the dust accretion, the dust production begins as being a dominating factor in the dust mass contributor, but as the galaxy evolves, this contribution, the contribution to dust mass is significant because of the accretion process, that is the grain growth in the ice cell. Similarly, between production and destruction, the destruction quickly becomes much more dominant over the productions of dust. And between the growth and the destruction of the grains itself, the model 5, we see that after about 8 gigayears up to the present time, this ratio is essentially has reached an equilibrium where the timescales are comparable. So for the model 5, the accretion timescales here are an inverse function of metallicity. So what that tells us that as the grain becomes more, the grain growth would become faster and faster as we go towards more enriched ISM. Whereas the destruction rate is a constant offset. So as the ISM enriches, the grain growth becomes increasingly efficient, and it is continuously offset by the destruction at a constant rate. And yes, so at the end, at the present day evolution, this gives us a very stable ISM for these galaxies here. That is all. I leave you here with the conclusions from both the parts. Thank you very much.
Yeah, thank you very much. Maybe I missed it. Any of these galaxies are interacting, or all isolated?
There is most of these galaxies are pretty isolated, except 5194, which has a companion galaxy, but it doesn't show any effects on our results.
Because I was thinking that the interaction might be generating a strong star formation event and then change more rapidly changing metallicity across the disk.
Yes, but the interactions are not that strong for us to see the effects.
Very nice thought, thank you. So, with the galaxies where you found that the young stars made a significant contribution to the dust heating, is there anything in particular that characterizes these galaxies that would allow you to separate them from these?
No.
It
just seems to be dependent, because all these galaxies also have different morphologies themselves. So it could be something with the sample is not big enough to
Okay. So the other question is that when you're trying to study the dust properties, but you seem to be severely hampered by the uncertainties in this alpha CO. So I was wondering, if you were to restrict yourself to the outer regions of galaxies where the molecular fraction is small, could you could that reduce your systematic uncertainties, or would you then have too small a spread of nebulosities?
We could, but the main issue with that would then be the coverage of metallicity maps that we have. So I don't think we have. So, just for example, this are the galaxies that we have, and the background is the star formation maps, and the white contours are where we have the metallicity measurements.
Yeah.
Okay, so for most of the galaxies, we don't reach the very outskirts. So it's not, at least by this data.
In your plot, when you have the models of the temperature,
against the complementary gas.
So which one?
It was back in the not the very first slides. Where you have those in the y-axis the temperature, below the temperature, and in the x-axis the condensate of gas. For two galaxies, I think one of them was the Whirlpool galaxy.
This one?
That one, yeah. So the upper one is the Whirlpool galaxy, no?
Yes.
Which is quite face-on.
Yes.
It's a big galaxy which indeed must have a central bulge that has all those stars.
Yes.
So you are looking clearly that part, no?
Yes.
And that's what drives the decaying part, no? The right part of the
Yes.
core. In the other case, I think this is a small galaxy, no? Something like a dwarf galaxy, which also is not as face-on as that one. It has a lateral.
Yes, it is not as face-on as the other ones, but
Yeah.
among the samples, we have galaxies with various inclinations, and we can see this even for galaxies that are relatively face-on.
Yeah, well, my impression is that, that the angle was quite large for this galaxy. I just Googled it.
Oh,
So,
I don't remember the inclination for that, but okay.
No, but the point is whether the effect is because you are not looking at properly at the central part of the board of the galaxy, or whether it's because that one is a small galaxy that has not evolved as much as the Whirlpool galaxy. You see what I mean?
The range
case,
is density is smaller.
Yes, but for the first part, it was just because of the inclination that the central part would provide much more radiation, radiation from star formation rate is what we that way. But if we look at like these examples here, in the center part is in fact the opposite of what we expect, where the older populations have much more contributions, and the stellar dominates more towards the opposite. So I don't necessarily think that the inclination could be the reason for that.
Now, the other thing that I wanted to ask you is when you plot the ratio or the alpha CO factor, and you show that there are galaxies that are below that one, yeah. So why you said that this is the dark routine, the CO dark? Because I mean, if you are destroying it because you don't have those and you are destroying the CO, then there is no need for CO dark. There is no CO dark.
I'm not saying that it is completely CO dark, but just saying that the amount of CO would trace much more molecular gas compared to these galaxies. So there would be pockets where the CO is not does not have the efficient luminosities. Does that make sense?
Well, you have a fixed amount of H2, and for the same H2, you have much lower CO because it's destroyed. So,
yeah.
So not all the CO is destroyed, but
CO dark meaning that the H2 is not well represented by CO. So it's dark as compared to CO.
Okay. That I wouldn't.
Not that CO is not there,
It's
just
not
that there's a lesser fraction.
That's what the people call
The CO dark molecular gas, no? So you have molecular gas, but you don't have CO.
Okay.
So you have H2, H2, but you don't have CO.
Okay.
dark to CO.
Like the CO won't efficiently trace all the molecular gas. So
No, the point is that because the advisor of Loran, I don't remember his name, in Baltimore, well, there was somebody who was arguing that there is CO that you don't see. No. There could be CO that you don't see, but that's another point. It is not the case. So that's what I was saying.
no, I don't know.
Okay.
More questions from Zoom?
Nothing on Zoom. I have a question. So thank you, very good talk. It's a comment more than a question. So you've considered many model-related effects and uncertainty. One of the things that I want to point out is also recent papers show that, so you're assuming a modified black body, right?
Yes.
Recent papers show that the dust opacity itself becomes a function of dust temperature. And the standard scaling that people use for the opacity I forget, 70 or 160 micron, is off. So the actual dust masses are then overestimated by up to a factor of 20.
Yes, the opacity does vary and it's not constant, but for the model that we're considering.
No, no, it's not just that the opacity varies, it's that the value that's used as normalization is off by a factor of 10 to 20, right? If you incorporate that uncertainty as well into your, I think you might, so one of the issues I find with the work you're doing is that you're doing a lot of model comparison, right? But I think that because the data does not incorporate the model uncertainties, you're seeing differences in models that probably aren't.
Yes.
Yeah.
Yes.
So,
but for the dust mass, there are various things like the draining prescription, the fuse prescription, and again. So even when a model has for a model with around a different dust prescription, we can see the effects of that offset that obviously.
well, yeah, but
for most of the things that I showed, they are all in the dust media things, so they do some things, so they do follow like comparably the same modeling.
right, but so for example, one of the latest plots you showed where you had the 5 and 9 model, right? Given the uncertainties in the data, I don't see a difference between the models, right? Yeah, see on the left-hand side, no, the previous plot there.
Yes.
Yeah, on the left-hand side, I don't see a difference between
Yes.
models.
Over
On the right-hand
here,
side as well, given the uncertainties in data, I would not say that these two models are distinguishable.
Because you say that you not take into account dust model uncertainties.
Even if you don't, if you look at the uncertainties in data that you have there, the error bars, they're actually off the order of the difference there. So it would only get worse if you incorporated other uncertainties. So my point is that this is all qualitative. If you did this quantitatively, you would know for sure whether or not there's a difference, right? So you could do, for example, you could do a hypothesis test here to show, to determine whether or not one model is significantly different from the other, right? So that way you know one way or the other.
yes, definitely, because in the paper itself, they which was then they were comparing the models to the specific galaxies and the observations, the same observations. Even there, they found that both the models were more or less a good picture, and neither one of them is one a better reality.
Okay.
There's no more question, but let's begin.
After, para quien se apuntó, el siguiente